let's look at chapter 1.3a, evaluating limits algebraically. So a couple of rules. First, limit as x approaches c of a constant will always be that constant. Okay, so no matter what x value we're approaching, if we're looking at a constant, we're essentially looking at a horizontal line. That horizontal line will always produce the same y value. Okay. Suppose limit as x approaches c of f of x equals to L. And if this is true, then any value, any constant that I multiply with the left side of that expression can be done on the other side of the equation as well. So b times f of x, limit as x approaches c of b times f of x is equal to b times whatever that limit is. Okay. To find limits for a function, algebraically, we're first going to try to plug the argument, that c value, into the function. If the resulting value is a real number, then the value is the limit. So whenever we want to evaluate the limit algebraically, the first thing that we always do is plug in that argument and see if we get a real number. If we get a real number, then we found our solution, and we don't have to work any further with the problem. So let's look at some examples here. Limit of x squared plus 3x as x approaches 2. First thing we do is we try plugging in the x value. So 2 squared plus 3 times 2, so 4 plus 6 is 10. So that's a real number. So that's our limit. Okay. Limit of 5 as x approaches 2. 5 is a constant, so there's no variables for us to plug in. So that constant will remain as 5, unchanged. Okay. Part C, limit of 3x to the fifth minus 2x squared plus 7x plus 4. We can plug -1 in for all the x's. So we're going to get -3 minus 2 minus 7 plus 4, and that will result with -8. Okay. Finally, limit as x approaches pi of x cosine of x. We plug pi in for x, so we get pi times cosine of pi. Cosine of pi is -1. -1 times pi will give us -pi. Okay. Now sometimes we're not, when we plug in, we're not going to get real numbers initially. So there are problems that we're going to have to do more work than just plugging in and finding a real number. Okay. So there's a canceling method. Okay, so the steps that we take here is we're going to still plug in the argument into the function. However, we may get a resulting value of 0 over 0. And if we get 0 over 0, that means there are potentially more things that can be done with the expression that will allow us to find a real number limit for the function. Okay, if we get 0 over 0, we're going to then simplify further using factoring and reducing or canceling. Okay, so here are the steps that we're going to take. We're going to first plug in the argument. Okay, just like we always take the first steps, regardless of whether it's going to work or not. We always plug in that argument and see what happens. Okay, so if we plug in the argument, if we get a real number, we stop because we have our limit. But if we plug in the argument and if we get 0 over 0, okay, that means we can potentially further evaluate the expression. Okay, so when we get 0 over 0, we're going to try then looking at the expression and seeing if we can find any common factors that we can reduce. Common factors that is shared between numerator and denominator. Okay. If we can find common factors to cancel, then we do that. Okay. And once those common factors have been canceled, then we try replugging in the argument into the reduced function. Okay. And if we plug in that argument, if we get a real number, then we can confirm that our resulting value is the limit. Okay. So using these steps, let's see if we can apply that for example 2. limit as x approaches -2 of x squared plus 5x plus 6 over x plus 2. So first thing we try is we just plug in the argument, plug in the -2. So when we do that, we get -2 squared, which is 4. 4 minus 10 plus 6, that gives us 0. If we plug -2 in for x, we also get 0. So 0 over 0, that means that we need to further evaluate, look for common factors, look to cancel, look to reduce, and see if that will help us get closer to the answer. So if we look at the numerator, x squared plus 5x plus 6, we can factor this, x plus 2 times x plus 3, and denominator is x plus 2. Now, there are common factors between numerator and denominator, so we take those out, which leaves us with x plus 3. So now we have our reduced function. So we're going to re-plug in the argument that did not work initially. So if we re-plug in the x, re-plug in -2, we get -2 plus 3, which is 1. So 1's a real number, so now we have the limit for this initial expression. Okay, let's look at some more examples. Okay, limit as x approaches 1 of x squared plus 5x plus 6 all over x minus 1. First thing we do is we plug in the x, plug in the argument. We get 1 plus 5 is 6. 6 plus 6 is 12. Denominator, we plug in 1 in for x, we get 0. Now 12 over 0, this is not in the form of 0 over 0, so that means there's not going to be any factors that we can cancel out. So this x minus 1 is not going to go away, regardless of what we do with the numerator. So here, 12 over 0, this is undefined, so we can simply say does not exist. Okay. Example 4, limit as x approaches 3. First thing we do is we plug in our target or our x value. So if we plug in the argument of 3, we get 3 squared, which is 9. 9 minus 4 is 5. Denominator, we plug in 3. 3 plus 2 is 5. 5 over 5 is 1, so that's our solution. There's no need to factor, okay, because when we plug in, we're not getting any troubles with our resulting value, so we can stop there. Okay, limit as x approaches 2 of x squared minus 4 over x plus 2. Here, again, we plug in 2 squared minus 4. 4 minus 4 is 0. Denominator, plug 2 in for x. 2 plus 2 is 4. 0 over 4 is equal to 0. Now, 0 over 4 is a real number, so we can stop there as well. This is our limit. So with example 3, 4, and 5, there's no need for us to continue any further after we plug in. Because here, when we plug in, we got undefined. Here, when we plug 3 and 2 into the respective functions, we got real numbers, so we stop.